Struggling with physics? You have come to the right channel. This is Physics is Easy with Mr. Jesse. The first part of this tutorial is on section 3 of chapter 27, entitled X-rays. For this part, we will cover the following objectives: discuss how X-rays are produced, determine the wavelength of X-rays, and find the shortest wavelength that can be produced by electron bombardment of a given metal. To start, X-rays are discovered and named by Röntgen in 1895. Later on, it was identified to be an electromagnetic radiation with short wavelengths. Now, the wavelengths the wavelength of X-rays would be lower than that of the ultraviolet light, and in fact it is typically at about 0.1 nanometers. X-rays have the ability to penetrate most materials with relative ease, and it is for that reason that we are able to see our internal organs or our bones when we are exposed to X-rays. So to know more about X-rays, let us view the video on the next slide.
So let us start by having a look at a real X-ray tube. This is the glass tube, which must contain a high vacuum. Otherwise, the electrons will collide with molecules of air, losing energy. At this end here, we have a hot wire cathode. The thermionic process results in the release of the electrons, which are accelerated towards the anode, which is at between 30 and 100 kilovolts relative to the cathode. When the electron hits the anode, it is decelerated as it collides with electrons in the metal. As it decelerates, it loses energy, which is released as an X-ray. The angle on the anode directs the X-ray beam towards this window. Here we have at this end the motor, which rotates the anode. Let us now go to a diagrammatic depiction of the rotating anode X-ray tube. The cathode is heated to cause the release of electrons. These are accelerated by a high voltage towards the anode, which is positively charged relative to the cathode. This whole process needs to be conducted within a high vacuum. Otherwise, the electrons will strike air molecules and thereby lose their energy before they reach the anode. When the high energy electrons strike the anode, they release energy. Some of the energy is released as X-rays, but most is converted to heat. To prevent the anode from melting, it is continuously rotating, and so the hot spot moves away from the electron beam. It then has time to cool down before it gets back to the position in the beam of the electrons.
If the electron loses all of its energy in the collision, the initial energy of the electron, which happens to be the kinetic energy of the electron, is completely transformed into a photon which has the energy equivalent to HF. So remember that in the previous lesson, the kinetic energy is just actually equal to E multiplied by the stopping potential, and that is equal to the energy of the photon, or HF. And since we're talking about all of the energy being converted, or all of the kinetic energy being converted into the energy of the photon, then we will have F maximum, which corresponds to the maximum energy of the photon. And expressing frequency in terms of C over lambda from the equation C is equal to lambda multiplied by frequency, then we could express E delta V as H multiplied by C over lambda minimum, or the minimum wavelength. And this is because if our frequency is maximum, then therefore our wavelength should be minimum, as they are inversely proportional. From this equation, then, we will be able to obtain the shortest wavelength radiation using the formula lambda minimum is equal to Hc over E delta V, where H is Planck's constant, C is the speed of light, E is the magnitude of the electron charge, which is 1.6 times 10 to the negative 19. And since it's just magnitude, then we don't put the negative sign. And lastly, delta V is the accelerating voltage. And now let us solve a sample problem that I have given in WebAssign. It reads, what minimum accelerating voltage would be required to produce an X-ray with a wavelength of 0.0280 nanometers? Now recall that our equation for the minimum wavelength is equal to hc over E delta V, where delta V is our accelerating voltage. So this is something that we are going to solve for. Now let's substitute our values, and we could simply solve for delta V. We have the minimum wavelength, which is given to be 0.0280 nanometers. So that's 0.0280 times 10 to the power of negative 9 multiplied by the Planck's constant, which is 6.63 times 10 to the negative 34, multiplied by the speed of light, which is 3.0 times 10 to the power of 8, divided by E, or the magnitude of the charge of the electron, 1.6 times 10 to the power of negative 19, multiplied by the accelerating voltage. So manipulating this equation would lead us to the answer, which is delta V, and that is 44,397 volts, or we could round it up to 44.4 kilovolts, and we have solved this problem. At this point, I need you to pause this video and work on the task on WebAssign called X-rays, and once you're done with the task on WebAssign, then you may proceed with this video. The next part of this tutorial is in section 4, diffraction of X-rays by crystals. For this section, we will cover the following objectives: describe X-ray diffraction and state Bragg's law, and apply Bragg's law to crystalline systems. At this point, I need you to pause this video and open X-ray diffraction Edpuzzle in Schoology, after which you may proceed with this video. Here is a sample problem on X-ray diffraction. This is question number 3 in WebAssign. The first order diffraction maximum is observed at 12.8 degrees for a crystal having an interplanar spacing of 0.280 nanometers. How many other orders can be observed in the diffraction pattern? Now recall, as when we discussed diffraction pattern, if we are going to solve for the total number of orders, we would actually set, or orders of diffraction pattern, we would actually set the angle to 90 degrees, and we would use Bragg's law to solve for M, which is related to the order of the diffraction pattern. So we will have M lambda is equal to 2d sine theta. So in order for us to solve for n again, we will set theta to 90 degrees. However, we do not know what our wavelength is, but we could solve for it given the rest of the givens in the problem. So we have 12.8 theta. So solving for lambda, all right, solving for lambda, we have the following givens. Theta is equal to 12.8 degrees. Also, it is first order diffraction, so therefore M is equal to 1, and we have the interplanar spacing, and that's D, that is equal to 0.280 times 10 to the power of negative 9 meters. Now let us substitute these givens to Bragg's law. We have M lambda is equal to 2d sine theta. Our M is equal to 1. Lambda is what we need to solve for. 2 multiplied by the interplanar spacing D, which is 0.280 times 10 to the power of negative 9, multiplied by sine of the angle, which is 12 0.8 degrees. So we could simply solve for our lambda. Make sure, by the way, that the mode of your calculator is in degrees because the angle is measured in degrees. So manipulating this equation, it would allow us to solve for lambda, and that is equal to 1.24 times 10 to the power of negative 10 meters. And now that we have our lambda, then we could solve for the total number of diffraction maximum we can observe, which is actually m. So we will say solving for m. Then we have m, our lambda, which we have solved in the first part. That's equal to 1.24 times 10 to the power of negative 10 is equal to 2 multiplied by the interplanar spacing times 10 to the power of negative 9 sine of 90 degrees. And this gives us m is equal to 4. So you have to make sure that you will round down your answer to the nearest whole number. So round it down. Therefore, our m is equal to 4. So we will observe a total of 4 diffraction patterns. However, the question says how many other orders can we have? So since we are already given that we could see a first order diffraction maximum, therefore we could see that there are 3 other orders of the diffraction pattern. And these 3 other orders of the diffraction pattern would correspond to m is equal to 2, m is equal to 3, and m is equal to 4, since we know that we have m is equal to 1. And the location of these different orders would correspond to theta 2, theta 3, and theta 4. And that concludes this tutorial. You may now proceed with the task and web assign entitled X-ray diffraction. Once again, always remember, physics is easy with Mr. Jesse.